not related to feeling better. So
Okay. Yeah.
um,
Go
what
for it. Anything.
what date is our final?
Let me look. I don't remember. Let's see. I don't think I have my calendar open. Nope, I don't. Just a second. Fatima says May 11th. And she's probably correct. Let me see for sure. Yeah, it's Monday, May 11th, 10 o'clock instead of 9 o'clock. I don't know why. That's the way they scheduled it. It's probably a better thing anyway. So anyhow, so a week, excuse me, a week from this coming Monday at 10 o'clock. And it'll be using sampling like we've done before. Anybody else? Anything? Okay. So then I'll share my desktop and we'll take a look at Blackboard, see if there's anything I'm not thinking about. Okay, I think we have resolved our sapling issues, but if anything comes up and you cannot get in there to do something, please let me know as soon as you possibly can. Best thing is probably send me an email and a text message, and then I'll put you with the guy at Sapling that I have met. He, I think, is going to be helpful if you need anything. Let's see, the issues that we've had so far that I know about. One person, their pop-up blockers were turned off, or excuse me, their pop-ups were blocked, and apparently Sapling uses that. And normally you don't want to allow pop-ups because then you get all that junk. I think you can do it selectively just for a certain website, so that's the way you do it, is just turn it on for sapling. Or you turn it on when you're doing sapling and turn it off. The other two, I never heard what the problem was, so I don't know. So anyway, that's that stuff. And then exam 4 is going to be next Wednesday. It's going to cover chapters 14, 15, and 16. So that's acid-base equilibria, equilibria of other kinds of reactions, and thermodynamics. A few questions from the previous chapters. And as before, be sure you can do everything in the presentations and everything in the worksheets. And then there might be some things taken from sapling. I'm expecting probably 25 questions or so, but I don't know. I have not gotten started on that, so I don't really know for sure. That's a weekend thing, I think. Okay, I think that's all that stuff. And looking at sapling, I extended these due dates out because of some of the sapling getting to it issues. So the thermo is May 2nd, and so is the electrochem, and the nuclear is May 4th, going into May 6th. Okay. So anyway, that's the current situation on sapling. If you see you're going to have a problem with getting things in, please let me know. Okay. I don't know if I can make any changes, but I should still know that. So, okay. So I think that's all that kind of stuff. while we were talking about that, anything you guys thought of that you want to ask about or comment on? While you're thinking, I'm going to see if there's anybody else I need to put in a group, because we're going to be doing a worksheet later on, I think. Okay, I think I got everybody in their correct groups and all that stuff. So I'm going to go ahead and just get into where I think we left off on presentations. And it looks like we were in chapter 19, the transition metals and coordination chemistry chapter. So that's chapter 19. So I'll put that up. So this is where we left off, was in this chapter, and it looks like we were on slide 8. So I'll go down to that. Tell you what, I'm just going to go through. I'm going to pop back in at this slide, and we'll just move from there. So when we were doing this before, this is about coordination, covalent bonds. They're not. Sometimes there's really not a way of predicting, at least not with your understanding of chemistry, to predict the number of ligands that you can put on a particular metal. It's pretty much coming from the geometry of what can be done. So in this case, you've got 6 ligands. Ligands are the waters. And the scandium in the middle here, it can support that many ligands. And then we had this slide where it showed 2 ligands, 4 and 6, but I was explaining that we're going to be thinking about this in terms of contact points. So for this first one here, there's 2 ligands, and you got one here, one over here, around the silver. And you also have 2 contact points, one from the nitrogen on one of the ammonias and one on the nitrogen from the other ammonia. And then for this molecule, the next one over, the ligand name is chloride. It's not a chlorine, it's chloride. There's 4 of those on this copper. So there's 4 ligands, and there's also 4 contact points. The contact point is coming from the negative charge that you have on the chlorine atom. And this last one, you're back to water again as being your ligand. You got 6 of those, excuse me, you got 6 ligands, and you got 6 contact points. The contact point being the lone pair electrons on the oxygen of the water. Now, water does have 2 lone pairs, but only have 1 contact point. So then we got into a situation where you could have 2 contact points on 1 ligand. So we got 2 contact points here on this ethylene diamine, or we abbreviate it EN, but it's 1 ligand. So we can then fold this up, and here is one of the ethylene diamines. I'm going to switch colors. We have another ethylene diamine over here, and then we have a third one down here. So that gives us 3 ligands, but each ligand has 2 contact points, or 2 contact points. So 2 times 3 gives you the 6 contact points altogether, producing a certain kind of geometry. And I think that was about how far we got. So we're going to look at some more examples. This next one, this is hemoglobin, carries oxygen to the cells and removes carbon dioxide from the cells. Does that using this iron that's in the middle here. The iron can change oxidation states in the hemoglobin, and that is how it's, selective for the oxygen and the carbon dioxide. And this is only one really large ligand molecule. Okay, but it's got 4 contact points. Each one of the nitrogens has a lone pair and therefore creates a contact point. Then another example, well, okay, now we're switching over geometry. Yeah, we'll come back to another example of something like hemoglobin here in a second. Here we've got water around, it's a cadmium cation. Or no, wait a minute. No, it's not. It's cobalt. I'm sorry. And they're showing this in terms of an ionic compound. So you've got the cation, the positive charge, and then you've got a chloride down here, 2 chlorides, and that's the anions. So they're illustrating it this time as a complete ionic compound. Previously, we were just looking at the coordinate covalent cation. So anyway, each of these has 6 ligands, 6 waters, 6 contact points. The next one over has 3 ligands. We saw this before with the ethylene diamines, and having 6 contact points altogether because, again, there is 3 of the ethylene diamines. So that gives us 6 contact points. And this last one over got chloride again. This time the metal is platinum. And each chloride has 1 contact point. So therefore, you got the same number of contact points as you do ligands. Now, all of these are going to produce a octahedral geometry. If you remember that from Chem 140. And it's easiest to see that, well, on either this or the one on the left. The idea is you have something in the middle, and then you have something above it, something below it, and then you have something coming out from the flat of the page. So if you can imagine, this is those wedges are trying to show that these 2 Y's are coming out towards you. You then have, if I can do this, you have another kind of wedge, except it's with hashed lines. This means these are back into the page. And so it looks like that. So this y and the x and the y, that's kind of linear. And then if we take what we have in the middle and rotate this a little bit, then what we'll see is that it's really making sort of a square where you've got the y's at the corners. So that's what octahedral geometry looks like. If we have rotated it so as to see this kind of representation, excuse me, then there is a y above the x and there is a y behind the x. Anybody got a question on that? So the reason why we have the 6 ligands, or actually 6 contact points, is because we can support an octahedral geometry with that platinum. Although I'm starting to get what we're really going to be doing in this class. If you want more of this, you would take an inorganic chemistry class. Okay, here's a little bit more on the geometry. We've got tetrahedral in this one. We have square planar in the other one. For tetrahedral, it might be easier to go back to methane because that was what we usually used for methanes, or for tetrahedral geometry. Do all octahedrals? Yeah, they're all going to have 6 contact points. Because like when I was drawing that octahedral geometry, I had a y above x and a y below the x, so that's 2. And then you had 1 at each of those 4 corners, so that's 4 more, so 6 altogether. And so that is the essence of octahedral. It looks like that. The way they name those, it's a little weird in a way because they're not real. It's not really coming from the way we're drawing it. It really comes from if you were to create flat surfaces between the various atoms. If we were to use those as like corners to a flat surface, you would make a octagon. But anyway, for tetrahedral, this is what you ought to be familiar with, is something that looks like this, where this hydrogen and this hydrogen and the carbon are all flat on the page, but then this hydrogen down here is coming out towards you, and then there is one that's going to the back. And for you guys are going to be taking organic, if you take this representation we have here, and then if you rotate it around the carbon, you can switch the hydrogens around. You'll always still yet have this angle that you're seeing here. So if you do a, excuse me, if you moved these 2 hydrogens to the positions that we have up here, they would have that same angle. And you can rotate it around and just spin it around and you would get that kind of geometry. So anyway, in this example here of tetrahedral, the ligand is cyanide. Okay, and then for this last one, we have square planar. They're doing it where they're showing the chlorine and the ammonia coming out towards you, and then a set going to the back. But you could just draw this flat on the page, and if we did, it would be like this. where your ligands is at a corner of a square. So it would, it would appear like that. And, if we connect those ligands together, we're getting a square. Hence square planar. Anybody got a question? Okay, then in that case, let's go to another one of the really large single molecule ligands. Good one we had. I don't know why it is drawing this in here. It's some artifact from Collaborate, so just ignore that. It won't appear on the version that you have in Blackboard. So this is chlorophyll, and of course, it is responsible for taking sunshine and it's in a plant. I'm sure Keon's loving my plant here. And it's going to take carbon dioxide and is going to produce various kinds of hydrocarbons, sugars in the plant, and it's going to give us oxygen. So, of course, that points out the dilemma of cutting down the rainforest and some of the other stupid stuff we do. Because, by doing that, we're increasing our loading of carbon dioxide. And fortunately, our need for oxygen is not that great, but having too much carbon dioxide causes a lot of problems. But anyway, the molecule it does that's chlorophyll. So you've got one big ligand. This whole molecule around here is the ligand. You've got 4 contact points. Those are at the nitrogens, like we've had before, where you have a lone pair of electrons on the nitrogen. And then the metal in the middle is magnesium. And it's switching oxidation states and performing this conversion of carbon dioxide into sugars and oxygen. So, and it by itself is not doing that, but it's capturing the sunlight and then transferring that on down. And there is one other, molecule that's kind of similar to this. I don't remember its name. It's a analog to the hemoglobin. Hemoglobin is in vertebrate animals, and then in invertebrate animals, there's a similar sort of molecule, except instead of having iron, it has copper. So that's why, like with a crab, for example, their blood is actually blue or greenish blue, turquoise, from that iron that is in their, what is their blood. And that molecule is performing the same function as hemoglobin. Okay, let's go to, I think, yeah, our lab compounds. And this is ethylene diamine. And in previous semesters, we did an experiment with ethylene diamine, or EDTA, where we were measuring calcium in water samples to see, what is the water hardness. You've heard of that phrase, you got hard water. and it makes it more difficult to produce sudsing, and it deposits calcium in the on the inside of the pipes, causes issues like with hot water heat and just other things. Anyway, a way of measuring that is doing a titration with EDTA. But EDTA gets used for a lot of other stuff. It is put in some cosmetics to take up any metals that happen to be in the cosmetic that would affect its, I don't really know, its use. It also, EDTA gets put in some food products, although it's outlawed in Europe, but we allow it here. Anyway, so it may not be a great idea. But anyway, it captures metals. So you can see here, instead of having a specific metal, it's just got an M, because the EDTA will attach to a lot of different kinds of metals, not just calcium. And if we were to unfold this molecule, we'd see that, it's sort of well, it's not really linear because it's got all these other functional groups going around there. But anyway, it does not look like what we're seeing if there's no metal in there. But it typically finds a metal and looks like this shape. So anyhow, it's one big ligand, and it has 6 contact points. For the contact points, 4 of those are a oxygen with a negative charge. So like up here. So it's the oxygen that has a negative charge. Previously, there would have been a hydrogen attached to that oxygen before it attaches to a metal. The other 2 contact points are the nitrogen lone pair electrons. So you see those back over here. So that creates sort of a cage-like thing, like all these do, to trap the metal. So anyway, that's pretty much the end of this stuff. Has anybody got a question on anything we've looked at? Okay, we're going to move on to just a couple slides, really, of applications of transition metals. So, and one of the biggest current applications is in catalytic converters in automobiles. So that, what we have here is our internal combustion engine here, the piston moving up and down. And we're taking in fuel and oxygen, and we are making some products. And we would like for those products to just be carbon dioxide and water. That would be the preferred thing for combustion. We'd like to just be making CO2 and H2O. But unfortunately, sometimes, instead of making carbon dioxide, we're making carbon monoxide. And as you know, that's really toxic stuff. It gets into the hemoglobin, in people, and replaces oxygen or carbon dioxide, and it does not want to come out later. So that's why if you take too great an exposure to carbon monoxide, even if you're taken outside to where the carbon monoxide is no longer present, your hemoglobin does not want to release it, and you can still die, even if someone has found you and you're still there, you're still breathing, but it's not going to be sufficient. The other product that we get are various nitrogen compounds. say nitrogen, and then I'll abbreviate CMPD for compound. So nitrogen compounds. Now that's not good either. This could be things like nitric acid or just things like that, and those are corrosive, toxic, bad things to have in the environment. And anyway, the catalytic converter is going to serve to get rid of those. So we have a connection to a oxygen. It says oxygen air pump. It's not just oxygen, it is really air, so it's got a small portion of oxygen in the air. But anyway, you're compressing air back at the engine, and then it's going down a tube and being injected into the catalytic converter. So now this oxygen here is going to combine with our carbon monoxide, and then it's going to take it to carbon dioxide, which is what we want to have. So that's one of the processes. It's also going to react with the nitrogen compounds. Well, the oxygen isn't, but the nitrogen-containing compounds are going to react on these various catalysts and get converted into nitrogen gas, which is going to be okay. That's not a problem. There's plenty of nitrogen. A little bit more nitrogen we don't care about too much. So anyway, the way that's done is with different catalysts. They're saying it can be rhodium, palladium. Those are two of your more common catalyst materials. Could also be platinum, cerium, iron, which that's pretty cool. That's cheap, and manganese. But definitely the rhodium and the palladium and the platinum and the cerium, those are extremely expensive. So that's why catalytic converters, $600, $1,200, $1,500, they're expensive devices. And I'm sure you know somebody who had their car jacked up and people climbed under it and they cut out the catalytic converter and stole it and then sold it. And I've seen recently where you can take your car to a muffler shop and they will weld in a thing that straps around the catalytic converter, and then I think there's a padlock or something like that that locks the catalytic converter down to slow them down on stealing it. They can still steal it, of course. You give them a little bit of time and they can do anything. But anyway, that's why catalytic converters are so expensive. It's those expensive metals. One other thing about catalytic converters is that these are all the metals. Since the metals are expensive, it's actually not a solid piece of one of the metals. Instead, there is a honeycomb shaped ceramic structure inside the catalytic converter. So it's looking like this. So that's what this down here is representing. And then the metal, there's a thin layer of it inside of these channels. So it's not just solid platinum or palladium. Even doing it this way, though, it's still a lot of expensive metal. And when your catalytic converter fails, what will happen is this ceramic part here will break and collapse, and your exhaust gases cannot pass through, is one of the possible breakdown scenarios. So anyway, that's maybe more than you wanted to know about catalytic converters. Anybody got a question? No. Okay, so our last part of our chapter is talking about magnetism. And magnets are made from transition metals, so that's why we're doing this. So let's go to that slide. So now a quick rundown of orbital diagrams. You probably would recall that we can have orbital diagrams where you've got some s orbitals and then you have some p orbitals, and usually you have things like a pair of electrons in an s orbital. And then if we're putting electrons into the p orbitals, and there's 3 of those at each energy level, you typically fill them single electrons first, and then if you have, say, one more electron, then you have to start pairing them up, and you get stuff like that. Well, to have magnetism, the first thing you're going to need for that to happen is to have unpaired electrons. If you don't have unpaired electrons, it's certainly not going to be possible to have magnetism. So the first thing you need is unpaired electrons. But then the next thing is, if we go back to our orbital diagram, say right here, where you have an arrow going up and an arrow going down, those are representing the spins of the electrons. And we would typically say that one is up and one is down. Okay? So that's part of this equation with these unpaired electrons. Are they ups or are they downs? Or are they a mixture of ups and downs? But then the next thing is that these unpaired electrons, those are in certain atoms, like here and here, here and here. What we're saying for 2 of these is that they don't have an unpaired electron. And then for the other 2, I'll get another color, for say these 2, they have unpaired electrons, but they're not pointed in the same direction like we see on the right side. See over here, they're all pointed parallel to each other, and they're all going in the same direction. So now we got to learn a few words. If you have unpaired electrons, but they're pointed in random directions, then we're going to say that it's paramagnetic. The spins are random. They do not line up with a magnetic field. And I guess maybe more importantly is that the para part means that it is not magnetic. So what we're seeing on the left side is not a magnet. You've got unpaired electrons, but they are not pointing in the same direction. They are not parallel. They are random. On the other hand, if we can get them parallel, like we see over here, they're all going in the same direction, parallel to each other, we now have a ferromagnetic material. Spins are aligned parallel to each other, so that would produce a magnet. Transition metals that will do that are things like iron, cobalt, and nickel. So most of the permanent magnets are made from those kinds of materials. Now there are two other possibilities that you need to be aware of, and those are on the next slide. So what we have on the left side, this is called antiferromagnetic. So it is ferromagnetic, but the problem is you've got one spin up and one spin down, and they cancel. So this material is not going to be a magnet. You've got spins that are parallel but going in opposite directions. Here's some examples of those kinds of materials. Again, they're involving transition metals, but these are not magnets. And then we got one more possibility. We went from ferro to Fe magnetic. It's got what's called unequal spins in opposite directions, so they don't totally cancel. If we look at, say, these two, we've got a red arrow going up, we've got a blue arrow going down, but the blue arrow is smaller, so it doesn't totally cancel. So some component of the red arrow remains. So you can almost do something like this. And those are all parallel and aligned in the same direction. So that would produce a magnet. So some of those materials are down here that would make a ferromagnetic material. Okay, so you guys are going to be good on those definitions and in recognizing if you have some information about spins, whether something is going to be a paramagnetic or ferromagnetic. Anybody got a question? Okay then, that is the end of this chapter, and yay, we are on our last chapter for this semester. So our last chapter is going to be nuclear chemistry. And, you know, a lot of the nuclear processes are the domain of the physicists. So we're going to be talking about some things that are really physics, but then there is a chemistry in there too. So anyway, it's a little of both. So we had a lab that we did on Monday involving isotopes. So you guys already know something about that. And then we talked about isotopes in Chem 140. So those should not be, you know, just a complete surprise to you. But we'll go over that a little bit. So with an isotope, oops, get my marker. What makes an isotope is the number of neutrons involved. Because the protons are always going to be the same. whatever is the atomic number gives us the identity of that isotope. So if you have 6 protons, or atomic number 6, it has to be carbon. It cannot be another element. If we change the number of protons, have a different element. But what gives you different isotopes is that you can vary the number of neutrons and therefore changes the mass of that particular isotope. So the nucleus is composed of 2 nucleons, protons and neutrons, but the protons are always going to be the same for a particular element. But each isotope can have or will have a different number of neutrons. Number of protons is the atomic number. Number of protons plus the number of neutrons together is the mass number. Now you remember when you did the simulation on Monday that there are mass numbers and then there is atomic mass, and those are 2 different things. They're similar. I mean, they're close, but the atomic mass is this decimal number. So we are actually considering what is the known mass of a proton, a neutron, and an electron. Where with mass numbers, we're just sort of rounding, in a sense, protons and neutrons to having a mass of 1 and electrons to having a mass of 0. So that is, mass number is more like a rounding or estimate of the mass. Okay? So this next slide is getting into why do we even have neutrons? Why neutrons? Because you could just go with, hey, protons and electrons, positives and negatives, and stop there. But that's not the case. And here's how that's going to work. If I have a proton, put one over here, and then I've got another proton that's together with it in the nucleus, that since they are both positives, they're going to repel each other. So they're not happy. They're going to repel. On the other hand, if we have neutrons, here's one neutron, here's another neutron, they're going to be attracted to each other. Let's see what would be a good color for attractions. I guess I'll just leave it blue. So one neutron is attracted to its neighbor neutron. Now this is similar to gravity, but it's not, it's not the same as gravity, but it's similar in that 2 objects having mass will be attracted to each other. And so the 2 neutrons, they do not have a charge, therefore they're not repelling, but they do have mass and they are being attracted to each other. Now let's throw in one more thing into our picture here, and that is, imagine what it would be like to have protons with no charge. Now, that's not a physical reality, but let's just say there's no charge. Well, then just like the neutrons, they would be attracted to each other. So since protons do have mass, there is some aspect of them that is attracted. The problem is they're both positive, so they're definitely repelling. So what if we do something like this? I'll put a proton here, put another proton right next to it, put a neutron up here, another neutron below it, and this proton is attracted to its neighbor neutron, and that neutron is attracted to the proton, and the other proton's attracted to that same neutron. This is going to get real busy if I'm trying to draw all the arrows are attracted to each other, and also the two protons have an attraction for each other if we are not considering that they are the same charge. So all these bodies are attracted to each other. However, you do have a repulsion between the protons because of their positive charges. So if the attractions are greater than the repulsions, everything sticks together. And if they don't, they're unstable. They want to come apart. So on the lower number of protons, that's around here. So we've got atomic number 20. And then on the y-axis, we have the number of neutrons. Actually, it goes up to 28, so it's a little bit above that. Anyway, we got 28 protons. We'll have 28 neutrons in the stable isotope. And you will have enough added attractions from those neutrons to cancel out the repulsions in the protons, and everything sticks together. So we have this first point here in our graph of number of neutrons versus number of protons. Neutrons on the y-axis, protons on the x-axis. So that takes us to this first part of our curve here. Now, they have extended the line upward if it were to continue to be 1-to-1, one neutron for every proton. But in reality, what happens is we start needing more neutrons as we get to a greater number of protons. So you can see now the line is deviating off from the 1-to-1. It's going to continue doing that until we hit a number of protons where it can no longer be stabilized by adding neutrons. And that is at about atomic number 83. And at that point, everything above, so going up through here, everything above is unstable. So those isotopes want to decay, as they would say, into lighter isotopes, into isotopes that have fewer protons. So our first point, everything there is 1-to-1. Above that point, the number of neutrons is greater than the number of protons until we hit this point where that will no longer stabilize the isotope. Has anybody got a question on how that works? So the stabilization of our isotope, what that's called is binding energy. That's what binds the protons and the neutrons and all that together. So that's sticking together your protons and your neutrons. And like we've already seen, there is a point where it's not good enough. But what we have here on this graph, this is the mass number and then the binding energy. And you can see that you hit a certain mass number about right there where the binding energy starts to decrease. Things start to decay, they start to fall apart. So these higher mass numbers that are over here, they want to break apart. That breaking apart is called fission, F-I-S-S-I-O-N. These isotopes are going to be decaying to lighter isotopes. Now, the other side of this is if we're at a lighter mass, so that's going to be these up to about here, those are going to want to combine and make heavier isotopes. That's called fusion. Unfortunately, that does not happen except inside of a star where there's sufficient heat and pressure to facilitate that process. So it doesn't normally happen. It would be great if it did because it'd be a much better energy source than fission like we have in nuclear reactors. But anyway, we haven't got that worked out yet, although there has been research on doing that. So anyway, there is an optimal point here of where we have the greatest binding energy. Okay? And that then is a determinant of what is the most prevalent element in the universe, and that happens to be iron. So whenever meteorites are found, they usually have a high amount of iron because it's the most stable element, has the highest binding energy. But like I said, we're not going to see, normally fusion. We're going to be seeing stable things, or we're going to be seeing things that break apart. So what we're going to be focused on now for a while is that breaking apart. But does anyone have a question before we start that? Okay, we're going to go through some of these decay, breaking apart processes, and then you guys are going to work on a worksheet to get some practice at that. So this slide shows you the different particles you can get. Now, there is one actually that we could put on here that's not here, and that would be the isotopes themselves. Although usually we don't think about that as being a decay particle. But in a typical decay process, you start out with one isotope, you end up with a different isotope, and then you have these decay particles. So some of the possibilities: alpha particle, beta particle, positron, proton, neutron, gamma ray. And we've got the symbols here, but I'm not going to get into that too much right at the moment because we're going to be hitting that again very soon, and it's going to be on slides that it's easier to see it. So not really going to spend a bunch of time there. And they're showing you how they're going to represent it in some of these pictures. And then what we have after that is a description of what these are. So if it's an alpha particle, it is basically helium. It's a helium nuclei. Has 2 protons, 2 neutrons. A beta particle is an electron. It's a high energy electron. It's moving very fast. If we have an electron, but somehow it has a positive charge, then that's a positron. Particle, same mass as an electron, but it has 1 unit of positive charge. And then a proton is the nucleus of a hydrogen atom. It's what we normally would think of as a proton. And then we already know what neutrons are. We've talked about that a bunch. And a gamma ray is from the electromagnetic spectrum. But you can think about that as being similar in a light. Got a whole energy. Yeah, somebody had a question? I heard something. I guess somebody just hit their microphone button. Okay, so now we're going to go to an example of our first decay process, and we'll just then be working through those. And I think, let me look here and see if that happened. Yep. Collaborate messed up some of the slides from this chapter, so we're going to have to go back and look at these using the slides that are over in Blackboard. So don't have to do that quite yet, but I will in just a moment. So here's an example of one kind of nuclear decay. So in this case, our decay particle is an alpha particle. It's got 2 protons and 2 neutrons. So its mass number is going to be 4. Its atomic number is 2. So it is really a helium nucleus. Now, you'll also see it written this way with the alpha symbol and a 4 and a 2. So we're writing out the symbols for these the same way that we would write out an isotope symbol. Okay? And our other decay particle really is this isotope over here, thorium-234. So we're starting out with uranium-238. We're ending up with thorium-234. Now notice that the mass is changing from 238 to 234. So we have lost 4 units of mass. But that 4 units of mass is in our alpha particle. So you can see how this is going to balance out. And we'll be looking back at that in just a moment of how you can balance these kinds of processes. Going back to our table here, we have alpha particles, which actually are going to have a positive charge. We're going to have beta particles, which is an electron, so therefore it's going to have a negative charge. And then gamma rays and some of these other ones, those do not have either charge. They're not positive or negative. So let's see how that was discovered. We've got a radioactive substance that's contained in a block of lead to protect everybody. And there's an opening in the block that allows then some of the decay particles to escape. So initially, we had the way they first did this is the Madame Curie experiment. She had radioactive materials. I don't think she had it in a lead. I don't know how she was doing that, but anyway, she had it in some kind of container, and she had a piece of photographic paper. And she put those in a drawer, came back the next day, and discovered there were spots on the paper that looked like the radioactive material she had in the same drawer. And she was able to, from that, figure out that, hey, the same way that you get an image on a photographic plate from light, she was getting an image from these radioactive particles that was hitting the photographic paper. So what we're doing in our experiment below that, we still have a photographic plate. We have our radioactive substance, and we get some spots in the middle of the page here, or the plate. But then they also added then a positively charged electrostatic positive plate and electrostatic negative plate. And what that did was they saw spots in a different area on the plate, and they were able to then come to the conclusion that there must be these particles, the beta rays, that have a negative charge and are therefore attracted to the positive plate. They also then saw dots in another location, the alpha rays, and they surmised those had to have a positive charge to be attracted to the negative plate. And then the gamma rays, they weren't attracted to either one, they just continued in a straight line. So they figured out that those must not have a charge. So anyway, that's how they figured that part out. It's from an experiment like that. So now going back to our decay particles, which then gives us our different processes. So we already seen an alpha decay. We did that with the uranium-238. This is below that's an example of a beta decay where you're getting an electron from it. Then we're going to have a gamma decay. And in that case, you're not going to see any change in the mass or the atomic number, but gamma rays could be detected. Positron emission, you're getting a positive electron, and electron capture, we'll get into that a little bit later. That actually is where we're moving an electron from the core electrons into the nucleus and changing the character of the nucleus. So we're going to break these down, go through each one of these separately, okay? And I think the best way to do that, because this next slide is totally messed up. Don't know what happened. Something went nuts. So I'm going to stop this and I'm going to start sharing my desktop, and we'll take a look at these. Let's see, how many slides is that? 1, 2, 3, 4, 5. These next 5 slides, we're going to look at those in Blackboard instead of here in Collaborate. So I'm going to stop that, and I'm going to share my screen. Okay, so going to Blackboard, course materials, lecture presentations, and I'll go down to the one for nuclear. Now the problem with this is I can't draw on these, so that's not going to be any fun, but otherwise it'll be okay. So here's our first decay process. So that's an alpha decay. So again, we're getting a helium nucleus. Its mass number is 4. Its atomic number is 2. The thing I want you guys to be looking for here is that the mass numbers and the atomic numbers are going to balance, looking at the right side and comparing it to the left side. So you see with uranium, you got 230, you have 238 in the mass number. Now, if you look over to the products where you have thorium, it's 234. The helium is 4. 234 plus 4 gives you the 238. The uranium has an atomic number of 92. The thorium has 90. The helium has 2. 90 plus 2 gives you the 92. So you can see how if you know 2 of these, you can always get the third one. So if you didn't know the thorium, but you knew the uranium-238 and you knew the alpha particle, then you could figure out what is the isotope produced. Or if you know what isotope is produced, you can figure out what decay particle must be kicked out. Or if you know the product isotope and the decay particle, you could figure out what isotope you started with, because all these numbers should add up. If you don't know what the element is, but you know what its atomic number is, you can always look those up on a periodic table and get those. Okay, you guys hopefully are seeing what I'm talking about. So let's go to our next slide. It's beta decay. So this is our high-speed electron. Again, the numbers are adding up. You have 131 as a mass number for the iodine on the left, and then you've got 131 plus 0 for the mass numbers or the products, so that makes sense. Or the atomic number for the iodine is 53, for the xenon is 54, but you have an electron in there that has an atomic number of -1. So if you combine 54 and a -1, you get 53. So the numbers balance. And then for the positron emission, same kind of thing. The mass numbers aren't changing for the two isotopes, so it has to be something that has no mass really, or almost no mass. And if you look at the carbon isotope, it's atomic number 6. Since the electron has a atomic number of 1, then the boron has to be, it's not really an electron, it's a positron. But anyway, the boron would then be the element that has an atomic number of 5. So you can see how these are all balancing out. And then we got electron capture, in which case you're actually taking an electron that is in the core, it's combining with the nucleus and making the product. So again, the numbers are balancing. Now the problem with electron capture is you have to pretty much be told that that's what's going on, because otherwise the numbers are going to look similar to what you would get for some other process. So that is not an easy one to figure out. And then neutron emission, that's usually going to involve combining two isotopes, like what we have on the left here. So you got californium and oxygen, and those are going to combine together, make a new isotope, and release some neutrons. So for a neutron emission, it's going to involve two different isotopes coming together. And that is the end of our examples of decay processes. So we're going to be starting up a worksheet, so I need to show you where that is. So going back here into Blackboard and looking at course materials and going down to worksheets and going to nuclear chemistry, you only have one worksheet. So here it is. And there's some information here at the top to sort of get you going on these. I mean, it's repeating some of the stuff I was talking about. But like for this first one here, number 1, you've got iodine 129, and it is releasing a beta particle or a high-speed electron. And you're going to try to figure out what is the identity of the isotope produced. So you're balancing numbers. So for the mass, you need to figure out what number would I put with 0 that would equal 129. And that has to be the mass number of the isotope. Or what number do I put with -1 to equal 53? And from that, I can get the atomic number of the isotope produced. And then when I know the atomic number of the isotope, I can take that number and look it up on a periodic table and figure out what element it is. I could even Google it if I, put in atomic number, whatever, and say what is the element that has the atomic number, blah blah blah, and it would give it back to you. Although you ought to be able to look it up on a periodic table because that's what you really should be doing. So you're going to need a periodic table. If I click back onto Blackboard and scroll down a little bit, click on periodic table, I get a periodic table. So that's one way of doing it. You may have another way to do it. So I'm going to stop sharing my screen here now. And first off, ask if there's any questions about doing this. I've got one person that came in since I was putting people in groups, so I need to get them in the right group. Okay. So I've got everybody is in your group. You see where the worksheet is. Let's see, I think it starts out. Let me look at that real quick here. I'll just put it up here for you guys and for a second. Okay, share files. So you're going to be doing the first 8 questions. That's what I was not sure about. So we're going to start out with these questions here, 1 through 8. And give you guys 10 minutes to work on that. And then I'll break back in and I'll ask a group, to tell me about what is the answer to number 1. Now I may break that down and do something like, what's the mass number of the answer to number 1? What is the atomic number of the answer to number 1? What is the element symbol for the answer to number 1? So we'll do something like that, but I'm going to give you guys 10 minutes to work on it, and then we'll start talking about what the answers are. Has anybody got a question about what you're trying to do? Okay, no one's saying anything, so I assume you're good on that. So I'm going to go ahead and start the groups up. If I put you in the wrong group, please tell me. And let's see what else. Oh yeah, if you have a question while you're working on this, let me know. And I'm scanning down through the groups here. Okay, got everybody. Okay, I'm going to hit start. Here we go.